Okay, great. Let's continue on our discussion about the arithmetization of algebra. So remember last time we were talking about Al-Khawarizmi, and he was the first one really to think about this idea of treating polynomials just like numbers. And the hint that we see that we're doing that is he talks about orders. So he talks about powers of x the same way as they talk about powers of 10. And so this is making that nice intuitive connection between a polynomial and a number. Because really all a Hindu Arabic number is a polynomial in 10, right? Instead of x, you use 10. And so that was great. Except he had a little bit of trouble in actually all the little technical details that you need to do. Particularly, he had trouble with subtracting a negative number from a negative number. And so the person who actually came along later and fixed up Al-Khawarizmi was Samaw'al. So he is 12th century. He was born and he worked in Baghdad, but he's originally from Morocco, so he wasn't Spain. This here tells us that he came from, I shouldn't touch it, came from Morocco. His father was a rabbi. He actually converted to Islam. He's actually another thing he's famous for because he wrote a book about theology, comparing Christianity, Judaism, and Islam together, and he decided that Islam was the way, and he converted there, but in secret, he didn't actually publicly convert to Islam until after his father died. The other interesting thing about him, he wasn't a mathematician. He was actually he's quite a famous doctor. Most of the books that he wrote about, he was a doctor, and actually late in life he just traveled between kingdoms, being like the doctor to princes and whatever. So he was quite well done. And he did his mathematics when he was like young. So he actually was 19 when he sort of finished with mathematics, and he published his results, and he wrote the book The Shining or Brilliant on Calculation. So I don't know, I don't actually know what this word al-Bahir, like if you put it into Google, into modern Arabic, that means the sea. So I don't know. I can kind of see why you might think the sea is shining or brilliant, but anyway, I don't know Arabic. And so he did his own study on Abu Kamel and Al-Khawarizmi, and afterwards he kind of mainly did a commentary on Al-Khawarizmi, where he sort of took Al-Khawarizmi's work and he kind of made it complete. So that was kind of cool. And so it's kind of interesting because he did this work by himself. So he wrote that he could only find people to teach him up to the early books of Euclid, and then everything after that he had to do as like self-guided study. So this is kind of showing that kind of maybe the golden age of Islamic mathematics was sort of coming to an end. So like there was all this kind of brilliance and people working in the maybe from 820 to around 1100, and after that mathematics became kind of less important. This sort of coincides with the with there being problems in the Islamic world. Mainly, things became more strict. they became more kind of inward looking. And this was caused by political pressures, right? Because we see that the Abbasid Empire was starting to shrink a little bit. It sort of broke off into various different kingdoms. There was the trouble between the Shias and the Sunnis. It's always kind of been a perennial problem. So there's this great pressure for orthodoxy, and kind of this resulted in a little bit more inward looking, and things like mathematics suffered because of that. But there were still some great mathematicians. There was Samaw'al, and later on we'll see Al-Kashi, who was perhaps the most brilliant of the Islamic mathematicians. He came along in around 1400. Okay, so good. I just wanted to check that was still recording. So what did he do in The Shining? So he wrote on binomial coefficients and Pascal's triangle. We'll have a look at that later. And the thing is, if you do Pascal's triangle and binomial coefficients, you are doing some kind of mathematical induction. Just, because the results are naturally talk about, you talk about, a recursive relationship that sort of goes on forever. The trouble is, of course, that he didn't really have the notation to be able to do mathematical induction. So most of you have done, Anna, have you done mathematical induction? No. Okay. So it's something that you do in math, usually in 200, right? Yeah. And so it's kind of like a technical device to prove things, and it's kind of very formal and technical. Maybe we'll do an example of it later on. But anyway, so it's very doubtful that he proved these results rigorously and formally, but it's obvious that he knew the results. So he must have done some kind of intuitive induction to get the results. So he talked about unknown quantities as orders, just like Al-Karaji did. And so we see, this idea that you get higher powers. And it's interesting, of course, because higher powers than 3 had no geometrical sense to them, although they still did these higher powers in terms of squares and cubes, which were, of course, the geometric things. Cool. And so, again, the number common to all orders is 1, and to each order is the corresponding part, with the property that any order times its part is 1, i.e. if you've got x to the n, you've got x to the minus n. Multiply them together, you get 1. So, how did Al-Samaw'al fix it all? So recall that Al-Karaji knew this, that if you subtract a negative quantity, that's the same thing as adding the positive quantity. But this was a problem, subtracting a negative quantity from a negative quantity. And this was what Al-Samaw'al said. So of course, remember, he didn't have formulas, so everything had to be done verbally, rhetorically. If we subtract a deficient number from a deficient number larger than it, there remains the difference deficient. But in the other case, there remains their difference excess. If we subtract an excess number from an empty order, the same number deficient remains. But if we subtract a deficient number from an empty order, there remains in it that number excess. What does that mean? Of course, it makes much more sense if we just write it down in terms of formulas. So a deficient number is obviously a negative number. An excess number is a positive number. So minus A minus B, right, is going to be a negative number if B, hang on, did I do this right? Right, it's going to be a negative number if b is less than a, and then that number is going to be minus a minus b. Whereas it's going to be a positive number if b is greater than a, and that number is going to be b minus a. It's just getting straight in your head what's going to be b. And that thing about the empty order, well, the empty order is 0, right? So 0 minus something is a negative, and minus thing is going to be positive. So this just sort of clears up the technical difficulties that Al-Karaji had. And so from that, you're now able to treat polynomials like you can treat numbers. And the thing is, if you've got something that's like a number, you can do arithmetic with it. That means you can add them, you can subtract them, you can multiply them, you can divide them, you can take the square root of them. Okay. We won't get into the square root, but you can do it. Okay, so one of the things he talked about was the law of exponents, i.e. that if you multiply two powers together, you add the exponents. And the way that Samaw'al illustrated this was he made himself a little table like this. And you have unit, that's a T, that stands for thing, mal cubed, mal cubed, cube cubed, mal cubed, cube cubed, cube, i.e. 9. And then on the other side of the unit, you've got part thing, part mal, etc. Okay, and then so kind of the way that you would read this would be like, if the thing is 2, then the cube is 8, and the part mal cube is 1/4 times 1/8 times 1/8. So he's using this to illustrate this law of exponents here, and he says the following. The distance of the order of the product of the two factors from the order of one of the two factors is equal to the distance of the order of the other factor from the unit. If the factors are in different directions, then we count the distance from the order of the first factor towards the unit, but if they are in the same direction, we count away from the unit. Okay, that's just kind of saying this, okay? So the product of two factors, and so by distance, he's talking about, how many squares away you are. So for example, if we multiply cube by cube, then we look, let's say cube by mal, how far away is the answer from cube? Well, you look at the distance from unit to mal, and you add it to there, and you get mal cube. Whereas if it's in the opposite direction, i.e. if one is a positive power, one is a negative power, then you go towards the unit. You go in the opposite direction. So it's exactly saying this thing here. So let's have a look at a few examples that, that he did. So what about finding part cube times part mal? I.e. in our terms, it's x to the minus 3 times x to the minus 4. We know the answer is x to the minus 7. So let's see how Samaw'al explains it. Since mal is fifth starting from the unit, we count starting at part cube and moving away from the unit 5 orders and end up at part mal cube. So he kind of explains it twice. Or equivalently, opposite the order of part of cube is 3, and opposite part of mal is 4. We add them to obtain 7, and opposite is the order of part of mal cube. So he's giving two different explanations of why this is true. The first sentence is kind of interesting. Mal is fifth starting from the unit. So he's saying so this really got me confused when I first saw it. So Mal is fifth. Does it look fifth to you? It looks fourth, doesn't it? But got to remember, this is the 12th century. They really weren't that comfortable with zero as a number, right? They were comfortable with zero being the empty order, just being kind of a placeholder, but they're uncomfortable with zero as an actual thing, okay? And so when they say fifth, what they're talking about is 1, 2, 3, 4, 5. So you count starting from the unit. So the unit counts as 1. Okay? And so this kind of makes sense, right? Because you want the unit times anything to be itself, right? Because it's like the identity. So the unit times cube has to be cube. So you start counting from cube, you count 1. And there it is. The answer is cube. So they're not comfortable with the idea of zero, kind of like you just do nothing. So it's the same reason why there's no year 0, right? You go from 1 BC to 1 AD. There's no year 0. So I think it's the same kind of concept as that. So after you accept that, then it's straightforward. So what is it? So it's fifth. Oh, so it's starting at part cube. So it's Mal is a fifth away from the unit. So we count 5 away from the unit because we've got both part cube and part Mal. They're the same order, so we go away from the unit. So we go 1, 2, 3, 4, 5, and there's our answer. The alternative way was opposite the order of part of cube is 3, and opposite part of Mal is 4. Add them to get 7, and opposite is the order of part of Mal cube. This kind of makes more sense because we're actually using now the numbers 3 and 4. We're actually using the numbers that are the power and adding them together like we want the law of exponents to be. And so he says opposite the order of part of cube is 3. So what it means that here is part of cube. Opposite is over here, is cube, and there is a 3 there. So here, I think he's using the numerals in their old-fashioned sense to be like numbers. Because remember, before the Hindu Arabic numbers came along, they used the letters as numbers. So this is just 1, 2, 3, 4, 5. That's just another way of writing 1, 2, 3, 4, etc. So that's 3, Mal is 4, you add them to get 7, but since everything is part, you're doing opposite, so the 7 is over here, which is G. That's how you get that. So here's another one. 3 parts of Mal multiplied by 7 cubes. Okay, so this is 3 parts of Mal is 3x to the minus 2. 7 cubes is 7x cubed. We want the answer to be 21x. Okay, so let's see how he gets that. We multiply 3 by 7 and 21 results. We find the order of cube to be 4th from the unit. So we count 4 orders from the order of part of Mal towards the unit. So the result is 21 things. If we want, we take the difference of the numbers opposite the orders of the factors, namely 2 and 3, and we find 1. And opposite 1, we find in the direction of the factor that has the largest number opposite the order of things. So what he's saying there is x to the n times x to the minus m equals x to the n minus m when m is bigger than m. When n is bigger than m, result is going to be bigger. Okay, so he's going into really more excruciating detail than we're used to, the law of exponents. And he has to do this, right, because he's talking in words. When you do it just in terms of symbols, it's kind of just like transparent, I think. Right? And that's why we use symbols. But if you're doing types of words, someone had to actually be the first one to go through all this gory detail and write explicitly what things mean. Okay, and so let's look at an example then of division of polynomials. And like, this isn't like a high school book, which would be, x squared plus 2x plus 1 divided by x plus 1. Some simple example like this. No, he has 20x to the 6th plus 2x to the 5th plus 58x to the 4th plus 75 x cubed plus 125 x squared plus 96x plus 94 plus 140 times x to the minus 1 times 50 x minus 2. A ridiculous thing divided by 2x cubed plus 5x to the 4th plus 5x cubed plus 10x squared. Okay? So again, I think the reason for this is you're not doing any formulas. So you've got to like do a meaty, I think the thinking is you've got to do a meaty example and go through all the details to kind of fully explain everything that could possibly happen. Okay. Down here, this quote here, I think really, again, drives home the point of what's happening here. We copied the divisor one order to the right, as we do in the Indian style of arithmetic. Indian style of arithmetic, that's exactly the stuff that Al-Khwarizmi did in his book on arithmetic. So he's just saying this thing, that dividing those top two polynomials is exactly the same as dividing numbers. Okay? He even thinks it's easier than dividing numbers, right? Because when you do arithmetic in numbers, you have to carry ones and stuff like that. You never have to do that in polynomials because you always, something times x squared times something times x cubed. It's always going to be something times x to the 5th. You don't have to worry about it carrying over to the higher order like you do when you're doing a power of 10, right? Anyway, so let me just remind you what's been going on here. This is something you would have done something like this in some kind of college algebra class. Okay, so what do? He explains here. We divide the greatest order of the dividend. So remember, you've always got dividend divided by, what's it, the divisor equals, what do you call the answer? Anyone remember? Quotient? Is it the quotient maybe? Okay, that sounds good. Okay, so here is the dividend, here is the divisor, and up here we're doing the quotient as we do it. So we divide the greatest order of the dividend, 20cc, by the greatest order of the divisor, 2c, and the result is 10c, right? So if you've got 20 cubed divided by 2 cubed, the answer is going to be 10 cubed. We place in the order facing 75, okay? We place it here because that's the cube column. Okay? So he's not writing any of the x cubed or x squares. He's doing everything in columns and he's just looking at the numbers.
So on the chart, it looks like your divisor starts with 2cc. Why is it going down to 2c?
Sorry, which one?
Okay, so up on top, your divisor
is this?
It's
yeah?
under 2cc.
Yes. Oh, because remember, that's what you do when you do division, right? If you're dividing 237 by 2, you first put the 2 there. So what happens is you put the divisor, and then here we copy the divisor one order to the right, as we do in the Indian. So every time you do, after you do a division, you move it down.
So they just originally pushed it over to the side, but it's actually starting at 2C.
Yeah, it's actually starting there, but since it's a divisor, you put it there, and the answer is CC divided by C, so the answer goes in C. Okay. So yeah, so it's only these two numbers where actually this actually applies to. This is just always going to be floating around. It's going to be changing as you move through. Okay. So next, what do? Well, you then multiply this by 10C and subtract it. Okay, so 10C times 2C is 20cc. And so the whole thing is, because the answer is going to be in C, everything has been pushed that amount to the left. So that's why it's okay to put there. Okay. Okay, and then we multiply this by 10C and we subtract, but it's 0, so we write down a 2. We get 5 times 10 minus that, we get 8. 5 times 10, multiply that, subtract that, get 25. 10 times 10 is 100, 25, and then there's nothing to be subtracted, so that then goes there. Okay, and then we copy the divisor one order to the right as before. And so now we've got 2 going into 2. So this is 2 mal cubed divided by 2, still divided by 2 cubed. So the answer is going to be 1 mal. So we write 1 in there. And now we subtract 1 times mal of this from that. So as we go along, we're just moving left to right the whole time. Okay? And it turns out that actually it divides into it perfectly. Okay? Which, who knew? And so there's the answer right there, right? Because here at the end we get 4, 0, 10, 10, 20, 2, 0, 5, 5, 10. We see that this is just double that. What goes there, and then we get 0, and so we end. Wonderful. Okay. The idea is quite straightforward. It's just division. It's a complicated example because it's long, not because it's complicated. You know, it's just like there's lots of steps. Al Samaw'al did this in the dust board. So this is actually sort of combining all the dust boards. So what you would do, right, is you actually only need these 3 rows here, because then you would rub out that line and put in that line, and then move the thing over, and then you would rub out that and put in that. And so it's actually very economical in its use of space. But it's the same, if you do it on paper, you would do it like this. If paper, you have enough room to do the whole problem. Okay, now we'll look at one more example. So what happens when the divisor doesn't go into the dividend? Then you're going to get a remainder, right? And we know from division that you can sort of go as long as you want. And typically what happens when you do division is, you know, at some point you repeat. So like if you do a third, you know, the answer will be that, or if it's a seventh, it's, I don't know what the seventh is, it's the 6 digits, and they just repeat again and again. Okay, so what happens when we got polynomials? It's a little bit different, but we still get a sort of repeating. So here it is. In the book, there's a mistake, which I corrected here because I shifted it one column to the right, as you see there, to make it, because he had this below that, which is obviously a mistake, right? Because each time you do it, you clear a column. Okay, so this one is easier to write down, so it's 20x squared plus 30x divided by 30x divided by 6x squared plus 12. Okay. And just from looking at it, you can see that it's not going to go in evenly. So he just goes straight ahead and blithely does it anyway. So 6 goes into 23 1/3 times. Subtract it. This goes into that 5 times. Again, you multiply and subtract it. This goes into that minus 6 2/3 time. And just continue going. And we see that the answer, he did it all the way up to the answer being, what did he get the answer being? 3 1/3 plus 5 divided by x minus 6 2/3 divided by x squared minus 10 divided by x cubed plus 13 divided by x to the 4th. Plus 13 1/3, sorry. Plus 20 over x to the 5th minus 26 to 2/3 x to the 6th minus 40 over to x to the 7th. And we still have stuff left over. Okay, and then he looks and he looks at the pattern that he's seeing. Okay, and if you look at it, you see here we get 3 1/3 minus 6 2/3, 13 1/3 minus 26 2/3. Here it's 5 minus 10, 20 minus 14. He sees a pattern. Okay. And he says, well, we must have the rule that, to get, so this one here, he says is, well, this must be minus 2 times that. And then proceeds to go all the way to x to the 28th. Okay. So he did this by the actual using the table there, and then the next 21 he just used by using that rule, and it turns out to be correct. I'm sure he double checked this, but he didn't put that in the book. Okay, and so this is the kind of thing that happens with polynomials. It's kind of the equivalent of repeating, like you get repeating digits. You get some kind of rule going for the coefficients. And he called this an approximation. This answer's being an approximation. And it's kind of true, right? When x is large, this is a good approximation. So, yeah. So really, he's shown that, and this also includes an example where you do a negative, I forget where it's, you get a negative number by subtracting a negative number from a negative number. Somewhere there. Anyway, so this is showing that polynomials can be treated like numbers. And so this is cool. Another thing he did was he did Pascal's triangle, binomial coefficients. And maybe now we know enough to be able to read some Arabic. Let's give it a try. Okay, so knowing that this is Pascal's triangle, you can kind of see, hopefully, I've got 1, 1 here, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Oh, there's a 10, I can recognize that. Okay, so if you recognize your Arabic numerals, you can see that it's Pascal's triangle. What are these things up here? Okay, this is Arabic, so that's a bit confusing, but what do we got? We've got a symbol here, we've got a symbol here, we've got a symbol here, and look, oh, look at that. This is twice those symbols. And then this here is this symbol and this symbol. And this symbol is this symbol twice. Okay, so this obviously must be thing, mal, cube, mal, cube, cube, etc. So this is giving the powers. So what this is showing is that if we've got A plus B, put it over here so the people back home can see. A plus B to the M is going to be A to the M, okay? Because the first number is always 1, the last number is always going to be 1. B to the M, and then in here we're going to actually have the binomial coefficients that we have. Okay, and so it's obvious that he has some idea of induction, right? Because we all know the rule that to get this, we add those two numbers. Like to get this number, we add those two numbers in the preceding thing. So this is sort of like a recursive inductive procedure to do this. Cool. Let me just finish up. Other interesting things that he did. So we remember Abu Kamel, he did this thing where he rationalized a irrational quantity. And so he showed that this irrational quantity is that. Not so much interesting in itself. We find these problems kind of boring and dull. But it's interesting because, again, he's doing things in an arithmetic way. That's an important thing. He came up with a formula to sum the first n squares. Again, this is kind of something we would prove by induction, right? So this had been proved before. I think Archimedes had proved this before as well. And another thing, when it came to number theory, that's kind of those linear equations, like ax by equals c. Say if you have a system of those, so you might have a system and you've got n unknowns and m equations. Okay, he was thinking of the cases when you've got some equations and you've got some unknowns. Well, either the problem can be necessary, possible, or impossible. So by necessary, that means that there's a unique solution to the problem. Possible just means that there are actually going to be a lot of solutions. So for example, this thing here will have lots of solutions. And impossible, meaning that the system is inconsistent. So for example, you can't have 2x plus 3y equals 1 and 4x plus 6y equals 17, right? Because you see that this is twice this, so this should have been a 2. So this is an impossible system. And so, for example, he looked at a problem where you have 10 unknowns and you have 210 possible sums taken 6 at a time, right? 210 being 10 choose 6, you found necessary conditions for consistency. Okay, so we don't want to go into that, but it's kind of interesting that this is the kind of problems that he was kind of dealing with. So he's really kind of extending the kind of math that had gone before. Okay, that's a good place for us to stop. And so next time, we're going to look at Omar Khayyam, or Umar al-Khayyami, and the treatment of the cubic.